Today we are taking a look at parametric equations applications. So applications of parametric equations. Okay. We are going to be using our calculator, our graphing calculator. Definitely need a graphing calculator for this one. And we're talking about just one application of parametric equations. There are lots of applications, but we're going to be focusing on one. And we're going to be examining the path of a projectile. Okay? So a projectile that is launched at a height of, I pronounce that h naught. It's h sub 0. That 0 means the initial. So that's our initial height, but I pronounce that h naught. Feet above ground at an angle of theta with the horizontal. That can be in degrees or radians. We're going to see for our problems, just to get a better idea of them, we're going to have that in degrees. So we're in our calculator, when I go to the calculator, we'll be in degree mode. And an initial velocity of v naught, feet per second. So note our units here. Okay, h is in feet, velocity is in feet per second, so time is in seconds here. The path of the projectile is modeled by this set of parametric equations. So here's our x and our y each time. Okay? We're going to be given we're going to be given v naught, we're going to be given h naught, and we'll be given the angle, the initial angle. Okay? This negative 16t squared is gravity's effect on the vertical position of the projectile in feet per second. Okay? All right. Okay, number one, let's look at an example. So we have a rocket that is launched from ground level. If it is launched from ground level, that means h naught is 0 at an angle of 80 degrees. So there's our theta, with initial velocity 95 feet per second. So that is our v naught. Okay. We're going to begin by writing the parametric equations. So my x of t will be v naught, 95, cosine of theta times t. My y of t will be h naught, which is just 0, which I don't have to write that, it's just 0, plus v naught, 95, sine of theta, theta is 80 degrees, t minus 16t squared. Okay? Okay. Now we're going to sketch the graph, so I'm going to go to my calculator. So here's how we're going to do this. I'm going to put my calculator, we're going to put our calculator into parametric mode. So when I turn on my calculator, go to mode, okay? Go to mode, and down here I want to go to parametric mode. It's right here. So I'm going to go down over, push enter on parametric. And our angle is in degrees, so I'm going to go up to degrees, push enter on degrees, so we're in the correct mode. Now, as soon as I go to y equals, when I go to y equals, it'll look different. Well, I already had one in there, but it'll look different. It's not y equals anymore. Now it's x1 of t and y1 of t. Okay, right now, anytime we push the X button, we're going to get t instead, because we are in parametric mode. Okay, so I'm going to input my x of t, so 95 cosine of 80, and then I'm pushing x, but when I push x, a t will pop up. Okay, because we're in parametrics. There's my x of t. Now for my y of t, 95 sine of 80 t minus 16t squared. So we have that in. And And now for my window. So we're talking about a projectile. So let's think about our window. So when I go to window now, I get T min, T max, T step. Those are my first ones. So think of T as time, right? T represents time here. So in seconds. So how many seconds do you think it'll take for this rocket to go up and then to land? I have no idea. So I think I'm going to make it a 6 and go from there. My T-step, I like to make this small. When the default is a pretty large value, I like to make this a little small. That way I get some really nice estimations. I don't have to zoom in. If I make this small enough, I won't have to zoom in, and that's nice. Okay, my X min. You're talking about a rocket, and this is the X is like wherever the rocket starts, it's going to go like that. So I usually start my X min at 0, just because I don't need to see anything to the left. There won't be anything to the left, so I'm just not going to look at it. My X max, I have no idea how far over this rocket is going to go. The angle is 80 degrees, so it's starting pretty steep. So I'm thinking it won't go all that far. I might make this maybe I might make it a 100, and then I can always play with it. The scale, remember, that's just hash marks on the x-axis. That really doesn't mean much. My y min. I like to see a little bit below the x-axis, so I like to start this at negative something. Okay, that just will allow me to see see over there nicely where the rocket in this case is hitting the ground. For my y max, this is how high the rocket is going. Okay, starting out at a pretty steep angle. Okay, it's going at 95 feet per second, which is pretty fast. So I think I need a pretty big number here. I'm going to make it a 200, and then I can always adjust from there. Okay, I might just set my scale at 50 just so I don't have a billion hash marks on the y-axis. Okay, let's graph it, see what happens. I very often have to play with this. I will warn you. I very often have to play with this. And I'm really shocked because it doesn't look like I'm going to have to play too much this time, and I'm not. Usually I have to play. I really do. Usually I have to go back and change my y max maybe, or my x max or something like that. But this time it worked out really well, so I'm going to stick with what I have here. I almost wish that I hadn't made it so nicely. Quite likely the next example won't be as nice. So you'll get to see me play with it there. All right, so I'm gonna sketch this graph. So I'm just sketching what I see here. Okay, and we want our window settings. So let's go to our window settings. T was 0 to 6. X was 0 to 100. And y was -5 to 200. And those settings produced this graph. Okay. All right. Estimate the maximum height obtained by the rocket. So we want the height, so that will be the y value here. Okay. So let's go. I'm going to hit trace. I hit trace, and when I hit trace I start way over here at time 0, and I will tell you that if you just do this, it takes a while. So instead of doing that, I can put in the number 3. I'm hitting 3 and then enter. When I do 3, it's going to take me to when time is 3. And when time is 3, gosh, again, I got really lucky here because it's already close to the top. Usually I have to play a little bit. But if I go to the left and to the right here, I'm looking at this y coordinate. I want to find the maximum that it can be. So I'm looking, as I scroll to the right, it keeps going up, it's going up, it's still going up. So I see here 136.760, 136.763, 136.762. So it looks like that is probably the highest, approximately. We could get a better approximation by zooming in, but I don't need to, okay? But I could do zoom in and then zoom in, or do zoom box. That's another way. But we're just looking for an approximation. So I'm good to approximate it like this, and I'm going to say that that is 136.763 feet. That's approximately the maximum height. Okay, approximate the maximum range. That's the horizontal distance the rocket travels. So we want the x value right here. So I'm going to trace again. I'm still on trace. I don't have to trace again because I'm still there. Okay, again, if you just press and hold this, it's going to take a while. So I'm going to jump there. I'm going to do 5, enter. And now I just jumped closer. Probably should have done 6, enter, but it's fine. Okay, so now I'm looking at the y coordinate here, and I want for the y to be 0. Right now it's 11 point something. So I'm keeping on going. I'm looking at this till when it gets to 0. Oh, it's 0.68. Now it's negative 0.2. Okay, so somewhere in between there, somewhere in between those values, y is 0. And y is 0 is when we're at that spot, correct? So it looks like it's probably closer to this than that. So I'm just going to say about, these are all approximations. So about 96.505 feet. Okay? So just approximations. We're just getting an idea here. Okay? We could get better. We could get a much better approximation by doing zoom box and boxing in around here, and that would take us in. We could get a much better approximation. A word of note, if I go to calc, second calc, I don't get my function. I can't find the maximum, I can't find the minimum, I can't do those things that we usually can do with that calculate button. Okay, it's different. All we have are some derivatives and values. Okay, all right. Estimate how long in seconds it takes for the rocket to hit the ground. Now we're looking for t right there. So I was already there. Hopefully I'm still there. I am still there. So t is about 5.85 seconds. Okay? So kind of an interesting application to parametric equations. Get to use our calculator a little bit, do some different things you may not have done before with our calculator. Let's do another one. We have an archer that releases an arrow from a bow at a point 4 feet above ground. So that's our H naught. The arrow leaves the bow at an angle of 25 degrees. That's our theta. With the horizontal at an initial speed of 200 feet per second. That's our V naught. So it's going fast. Our rocket was going at 95 feet per second. It must not have been it was not a very strong rocket. This arrow is going faster, so it should go farther, right? Okay, set of parametric equations. X of t will be, all right, the V naught cosine of our angle all times t. Y will be H naught plus our V naught, initial velocity, times sine of our angle, all times t, minus 16t squared. So those are going into my calculator. I'm going to put these in. clear what's there. Okay, 200 cosine of 25. I'm going to close the parentheses on the 25 and then just put the t. Don't really, when you put it in your calculator, you don't have to have those parentheses there. Okay, that t will not be part of the cosine because it's outside of the argument. Okay, and then our height plus 200 sine of 25, close parentheses on the argument, and then multiply by t, minus 16t squared. And now for our window. You do have to play with your window every time. Okay, how long do you think the arrow will be in the air? I don't know. I'm going to just leave it on 6 and I may have to adjust. How far do we think the arrow will go? I think it's going to go pretty darn far. I don't know, maybe 700 feet? I don't know. Okay, y min, I like to start negative. Our angle is only 25 degrees. So how high do you think this arrow is going to go? I'm thinking not to 200. I don't think it's going to be close to 200. I think I might do 100 and go from there. So these are just some initial guesses. And like I said before, I almost always have to play with my window to get a good picture of what's happening. So there's my arrow. I've gone off the screen, but I do see where it's starting to come down. So I think I know I need to have more y's, and I need more x's too. So I need more y's and more x's. I need a lot more x's. I think I'm going to try going up to 1,000. For my y's, I think I'm going to go up to maybe 130. See if that's enough. And it is going to be enough. Good. See if our x's are enough. Ooh, just barely. I'm getting really lucky on here. Sometimes I get luckier than most. Alright. Notice that this is starting a little bit above the origin because we're starting at 4. Okay? So know that. So I'm just going to copy my graph. Okay, noting that I'm starting above the origin. Okay? Let's write what our window is. Our t's are going from 0 to 6, and I may not have needed all those t's. Let me see what happens if I just go to 4. Let's see if going to 4 is enough. Oh no, it's not enough because it stopped. I needed more time to hit the ground, right? So maybe going to 5 we'll go to 5. But will that be enough? Let's see. Almost. So I'll just go to 6 like I had it. And I know that'll work because we already did that one. Okay, our x-min was 0. We went from 0 to 1,000 feet. Our y's were going from -5 to 130 feet. Okay, let's answer the questions they ask. Approximate the maximum height in feet that the arrow reaches before starting to come back down. So we want this y value. So I'm going to trace, and then that's going to be about 3, so I'm going to do 3, enter, and then scroll to the top. I'm looking at my y's. I want to know, I know I'm going up still here, so I want to know when does it start to go down. I've hit 115. Still going up. I'm still going up. Oh, I started to come back down. Let's see. 626, 628, 627. So 628 here. So 115.6288. So I'm going to round that to a 9. So about 115.629 feet. About. Assuming the ground is level, estimate the horizontal distance the arrow travels before it hits the ground. So we just want the x coordinate there. So back to my calculator. I'm still tracing, so I'm going to do 6, enter. It took me off the graph, but I expected that, so I'm going to the left, still on the curve. I'm just going to the left until I can see my cursor again. There it is. Okay, I'm at negative 0.89, negative 0.03, and 0.8. I think that negative 0.03 is really close to 0. So I'm going to say this is about the x coordinate 966.124 feet. So that arrow went far. Okay, one more example. I went and looked up some stats on Minute Maid Park to get some realistic numbers here. Okay, a baseball is hit in Minute Maid Park at a point 3 feet above ground level. So the batter is at home plate and he hits the ball and the ball takes off. Okay, it leaves the bat at an angle of 24 degrees. 3 feet will be our h naught. 24 degrees will be our theta, with an initial velocity of 92 miles per hour. We're going to have to do some converting because we need feet per second. Our equation only works for feet per second. So we're going to have to change that 92 to feet per second. Okay? Taking off towards left center field where the 25-foot wall stands 375 feet from home plate. Okay? Let's write a set of parametric equations describing the situation. So the first thing we have to do is get that 92 miles per hour to be feet per second. So let's do that. Let's do a little conversion. So right now we have 92 miles per hour. So I set that up like that. 92 miles per 1 hour, right? And now I'm going to do some unit analysis here. So I have miles per hour. I want feet per second. I think I'm going to take care of the miles first. Okay? There are 5,5280 feet in 1 mile. So since I have miles on top, in my conversion, to get rid of miles, I need to have miles on the bottom. So in 1 mile, there are 5,280 feet. So our miles will cancel and I'll be left with feet. Alright? So right now this will give me feet per hour. I don't want feet per hour, I want feet per second. Now I need to get rid of the hours and make them seconds. Since hour is in the denominator, I'm going to make sure hour is on top. So what do we know about hours if I want seconds? Do we know how many seconds there are in 1 hour? Well, I know in 1 hour there are 60 minutes. And I know in 1 minute there are 60 seconds. Okay? So, look at our units. The miles will cancel. The hours will cancel. The minutes will cancel. I will be left with feet per second. That's how you do a unit conversion. Okay? Now, in my calculator will take care of the numbers. So I have 92. I'm going to go to my home screen. 92 times 5280 divided by 60 divided by 60. And I get that decimal. I'm going to convert that to a fraction. Math, enter, enter. That way it's going to be easier for me to type into the calculator. So this is feet per second. So that is our V naught. Okay? So my x of t will be V naught cosine of my angle times t. My y naught, I'm sorry, okay, my y of t, x of t, y of t. Sorry about that. I think I've done that before on you. Okay, y of t and x of t. This will be our initial height, 3, plus v naught, sine of our angle, times t, minus the effect of gravity, so minus 16t squared. Okay, that's what's going to go into our calculator. Okay, 24 divided by 15, cosine of 24 degrees for x of t. For y of t, 3 plus 24 divided by 15, sine of 24 degrees times t, and I just realized I forgot the times t up here. Minus 16t squared. Okay, I'm doing a quick check to make sure I typed it all in right. I think I got it right this time. Okay, so let's go ahead and see what kind of window we're going to look at. So we want to know, so I know down here, we're going to sketch the graph. We're being asked, does the ball go over that 25 foot wall? Yes. The wall stands 375 feet from home plate. Okay, so in my, I don't know how long the ball will be in the air. I don't think it'll be 6 minutes though. Maybe 5. I don't even think it'll be 5. I think it's going to be more like 4, but we'll see. Okay, I don't need to go all the way to 1,000 because the wall is 375 feet away. I'm just going to go to that wall. I'm going out to center field or left center field, whatever. Okay. How high do we think the ball's going to go? How many feet high? I'm not sure. I'm really not sure. I don't think it'll be very, very far. I might try 100 and then play with it if I need to. So let's see what we get from this. So there's the ball. It's going. And the question is, did it go over the wall? Well, first of all, that graph is pretty good. I'm going to go ahead and sketch that graph. That's not a bad one. It certainly looks a lot like this picture over here, doesn't it? Okay, so there's my little sketch of the graph. And I'm just going to stop at 375 because that's where the wall is. Okay, so I'm curious, is that 25 feet or not? So before we do that, I'm going to go and enter in my window. So my t's went from 0 to 5. I may not have needed all those, but that's fine. My x's go from 0 to 375. My y's from -5 to 100. Okay, now let's see if this ball went over the, let's see if we got a home run or not. Okay, so back to our graph. I'm going to trace and I'm going to go over. So let's see, 4 maybe? Oh, 4 is already off the curve. How about 3? Yeah, ooh, 3 is almost there. So I really only needed to go to about a little over 3 seconds on my time. So I'm going to go to 375. So I'm going to go to 375. There I am at 370, almost 3. I'm actually at 376. I'm at 376 and I'm already at y equals 21. The wall is 25 feet and I'm lower than the wall here. So the ball does not go over the wall. So I will say, let me come up here to my little sketch and say this is about, let me go one more here. No. this is about 22 feet. That's approximately the y value. So does the ball go over the wall? The ball does not go over the wall. Okay, why? Because at about x equals 375 feet, y is approximately 22 feet, and the wall is 25 feet. Okay? Change the angle to 25 degrees. Does this change the outcome of the at-bat? Well, if we can easily go in and change in our y equals, in our equations, we can go in and change x of t and y of t. Just go over and change it 1 degree more to 25 degrees for our initial angle. Let's see what effect that has. Okay, so I'm going to trace. I'm going to go to 3 again. Okay, and I'm looking here. I want x to be 375. At 375, we're at 27 feet. About. I know this is approximating, and we could get closer, but this is about. I'm pretty sure that this ball, because if I go one more over, I'm at 376 feet, and I'm still above the wall, right? So does this change the outcome? Yes, it does. We got a home run. So when x is 376 about feet, change that to approximately equal to, y is approximately 27 feet. So the ball goes over the wall, and we have a home run. Okay. Interesting stuff, I think.